The charges are Q1 and Q4 equal, and Q2 and Q3 are equal. What is the net electrostatic force on particle? Wait, oh, what is Q if the net electrostatic force on particle 1 is 0? Is there a value Q that makes the net force? Oh, wait. Oh, Q2, Q3 and equal Q. Oh, okay. Sorry. I get it now. Okay. Okay. So what is Q if the net electrostatic force on particle 1 is 0? Is there any value of Q that makes the net electrostatic force on each of the 4 particles 0? All right. So what do you guys got so far?
I don't have much.
I haven't done, but I haven't done, and I was really annoyed because I did the problem and I did it correctly to an extent. I didn't have my calculator in radian mode. So
Oh yeah.
I'm not sure which mode it is, but I had it in the wrong mode and I put it in the right mode and had the right answer. So I was a little annoyed by that. But
oh, so you did get the right answer for this one?
well, so I used my third attempt, and once I like put in my third attempt and like it was wrong, I realized that my calculator was in the wrong mode.
Oh,
So I got partially correct.
Oh, so what you need is you need more attempts so that you can put in the correct answer. Is that right?
Yeah, but I mean, like I
feel like it's no big deal.
I don't know how that all works. So
well, so the way that it can work is I can give everybody more attempts. I was gonna do that anyways. So what I'll do is I'll turn the number of attempts up to 7. And so then you can go ahead and put the right answer in, because I don't care how many attempts it takes you, as long as you do it. So
yeah,
I set that too low for this assignment. So I'll increase the number of attempts to maybe 7 or 8.
Well, it was me just having a low moment. So like, I mean, 7 might just make people feel like they're not stressed on the third attempt to try to get it.
Yeah, that's fine. I don't care. It's not supposed to be super stressful. It's supposed to be so you can learn how to do it. So all right, I'll increase the number of attempts. It just 3 was the default, and so I should have increased it, but I'll fix that. Okay, so you know how to do that one?
I knew how to do that one.
I was just struggling a bit, just like in terms of, I guess, where to go. So like, I know we have to find the individual pieces for, I thought for each of the particles, but there was something really, I need to find like the F, like if I was finding the force acting on particle 1, I really only need to focus on one particle to necessarily get the question.
Well, you really only need to focus on like one direction. So either all of it in the Y or all of it in the X, because then you could just solve for it.
Okay. Yeah, so I was just more confused on, I guess, just the entire question.
Oh, okay. Well, it sounds like David knows what he's doing, but just in general, you want to separate out the X and Y components of the force. And then you want to say, all right, if the net force on particle 1 equals 0, then that means that the X and Y forces have to be equal and opposite.
Okay. So like, would the F, okay. So because the force is acting on it, like you use the fx and fy functions to find that, I guess, resultant kind of force vector, like the
Hey, David, could you move your computer or whatever a little bit closer so I can, I'm sorry, I can't, I'm having a
Yeah,
hard
no,
oh
time.
yeah,
no
sorry.
worries.
I also mumbled too.
No, it's
so,
okay.
so that was my bad. Just like the fx component, is that a specific other particle acting on particle one that I would have to, like, I could rewrite like the force, the x force acting on particle one, would that be from particle two acting on it? Okay.
Yes. So,
Okay.
yeah, which particles contribute an X component to this problem?
It would be particle two and particle four,
Yes.
both acting in the x and y direction on.
Exactly. So you would say, all right, my total force is equal to 0, and that equals the force on particle 1 from particle 2 plus the force on particle 1 from particle 4. And those
Okay.
two X forces have to equal 0. And then you should be able to solve for it that way. And you do the same thing with Y.
Okay. Okay, that helps. Thank you.
And then do you guys know how to do the second part, or?
I'm sure if I, like, once I actually do the first part, I should be able to
Okay.
do that. So it's saying is there any value of Q that makes the net force on each of the four particles 0? So would you just have to set the total force would be 0, or?
You'd have to find values for Q2 and Q3 so that the whole system would be at equilibrium.
Okay.
And so they would all be equally attracted to and repelled by the others.
Okay. That makes sense.
If that's even possible. But this may be a configuration that might not be possible to be in equilibrium like it is now.
Okay.
So I guess everybody's studying pods. What about you new guys? Rebecca, do you guys have any questions?
Hi, I don't know, I kind of was looking, like jumping around, like I have all of them up to 6, but like 7, 8, I have 11, but like the higher ones I don't have. So I'm just, okay, because I know for 12, I was looking at it and I was just confused, like, wait, let me find my work. Oh yeah. I was just confused, like, do you go from microcoulombs over meters cubed to electrons, like by dimensional analysis? Because that was like the only way I like, that was my idea of going about it, but I don't really know if that like makes sense with the density. Like, I don't know if there's like some sort of rule that makes it easier, but
Oh, let me read the problem real quick and then we can talk about it. So it says a charged non-conducting rod with length 2 lies along the positive side of an x-axis with one end at the origin. The volume charge density rho is charge per unit volume in coulombs per cubic meter. So how many excess electrons are on the rod if rho is uniform with a value of 4.33 microcoulombs per meter cubed, and be a non-uniform with value given by rho bx squared. Okay, so let me switch over to my my video camera so I can show you what I'm doing. Is that okay?
yeah, that'd be great. Yeah, I guess also like the uniform and non-uniform, like the fact they specified it, I figured there was something behind that, but I just didn't because like just doing dimensional analysis, you don't really take into account whether it's like distributed uniformly.
Yeah, that's true. So for the first one, what it's saying is that the charge is evenly distributed throughout this rod. So let me draw my rod here. Okay, so we have a rod, and if it's uniformly distributed, that would mean that there's a little electron stuck everywhere throughout the volume. So the charge density, what's charge density equal to?
That's the charge over volume.
Yeah, so it'd be the total charge Q divided by my my volume. Okay. And so it tells you the dimension. So it tells you the cross-sectional area here is equal to 4.88 centimeters squared. And the length is 2.43 meters. Okay, so we can get our volume from that. And then it tells you that the charge density is uniform with the value of, so it'll say 4.33 minus 4.33 microcoulombs per meter cubed, right? So if you, and what we're after is Q, right? The total charge. And if we know Q, then we know that Q is equal to N, the number of electrons, times E. Right? So if we take our volume and multiply it by the charge density, that will give us Q for that one, right?
Yeah.
And then you can divide your Q by the charge of one electron, and that'll tell you what N is, where N is the equal to the number of electrons. Oh, yeah. Number of electrons. Right? Does that help with the first one?
Yeah.
Or?
Yeah, that definitely makes it a lot easier because I felt like I was like kind of, I didn't really know what I was doing. So, but yeah, that makes it a lot easier. So then what does it mean if it's not uniform? Does that mean you can't use that like relationship?
So that means it's not as convenient. Okay. So it says non-uniform with the value given by rho equals bx squared. So I'm going to write this down. Rho equals bx squared. And then we know what B is. It tells you B is equal to minus 1.33 microcoulombs per meters to the fifth. Okay. All right. So what do we need to do to solve this one? So if it's non-uniform, then we need to integrate?
Ew. I guess so, yeah, because you can't just use like, you can only use, yeah, I think you have to integrate it if it's not constant.
Right, because we've got to find the charge density over the shape. And let me draw, okay, here's my, so that has this funky thing. So here's our, let's say that this is our X direction, right? Let me go back to the problem and see what it says. It says that the value of rho times bx squared. Okay, so I guess okay, so it lies along the x-axis. Okay, so here's our x-axis, right? And as we go this way, so as we start over here, so here's our function, right? It's b equals rho x squared. So over here, that means at x equals 0 right here, then there's no charges. And as we go across here, the number of charges increases as a parabola. So we've got rho x squared there, right? So then we need to do an integration over the volume, right?
So you do like from x equals 0 to x equals whatever the length of the rod is.
Yes. Yeah,
Okay.
that's exactly right. So we'll have, all right, here's our charge density. And then we're gonna say, we'll say N equals Q over Q over minus E. And then we'll say, so this is the number of electrons. And then we're gonna, we'll change Q. So Q, did you read about the volume charge element in the book at all?
Was that in 21?
It should be in 21.
I probably read it, but I don't remember exactly what they said about it.
Okay, so if we have Q here, we could just as easily say that we have rho times dV. So this would actually be dq dV. So this is the integral that we're going to need to solve, and this is our volume element. Okay, so let me move the camera down here. Okay, and now we could, if we go back over here, we can say that N equals dq over minus E, right? And we can write this as rho is constant divided by minus E, then times the integral of dV. So we're going to need to integrate over our shape. Oh, and actually the rho should go inside of the integral here. Okay, so everything is constant. Okay, so we're gonna have 1 over minus E, then we'll have b times x squared, and we're gonna integrate along x, right? And we've also got to integrate around the circle here. So the first one is dx is going to go this way. We've got to integrate this way. But then we're also going to have to integrate over this area here. So we'll say that this will be d, we'll call that dA. So what is dA equal to for a circle? Because that's our the end here.
Yeah, pi r squared.
Pi r squared. That's right. So we'll have dA here, and dA is just if we integrate it over the surface area of a circle. So that'll be pi r squared, and that comes out of here. And we actually know what dA is, right? Because it told us that in the problem. It said the cross-sectional area is 4.38 centimeters squared.
Mm-hmm.
Let me go to this other page over here. Sorry, it doesn't all fit on one page. Okay.
Well,
Okay, so we got this. So we are gonna have the number of electrons is going to equal B times A divided by minus E times the integral of 0 to L, and L is the length of our cylinder, times x squared times dx. Okay, so what is the integral of x squared in general?
so it'd be x cubed divided by 3 plus c.
X cubed divided by 3, and then what did you say? Plus c?
Yeah, I don't know.
Okay. Yes, I think we can set our constant equal to 0
Yeah.
because and we'll say we're going to integrate this from 0 to L, right? Those are the limits of our integration. And so we'll end up with B times A divided by minus E times L cubed over 3.
Hmm. So at that point, you just plug stuff in, and then that'll give you those.
Yes.
Okay, cool. Yeah, that makes sense. Thank you.
So yes, physics with calculus is fun.
Yeah. Yeah, I'm trying to think of other problems. Well, if anybody else has questions too, I don't want to like take up all the time.
Oh, we have 7 people here, although everybody has their face cams off, which is okay. But hello, everyone. Thank you for coming to office hours. Hey, Shane. How's it going? And hi to everyone else also that doesn't have your face cam.
Going good about yourself.
All right. So, what other problems did you guys want to look at? Or what other questions do you have?
Could you talk through number 4? I was just a little confused by, so like for number 3, how you're talking with Abby, like it was, there's only the one particle that's 0. How much different when it's two different particles that are both 0?
Wait, say that again.
So for number 4,
Uh-huh.
it says that the net,
Oh, the net
it's the same
electrostatic
square.
force on particle 1 and 4 is 0. What is big Q over little q? All right, let me share my my screen real quick so we can take a look at that one. Okay, here's the problem. So in the figure, four particles form a square. The charges are Q1 and Q4 equal big Q, and Q2 over Q3 equal little q. All right, the net electrostatic force on particle 1 and 4 is 0. So what is big Q over little q? Okay, so I'm gonna draw this problem because that always helps me to visualize things or to understand the problem better. So even though there is a picture there, I still always like to draw it. Okay, so because in the picture they don't really put the which one is big Q and little q. Okay, so here's my cube. And then it says 1, 2, 3, 4. And the problem says that, so big Q's up here in the corner and down here. And then these are my little q's. All right, so what did you do so far?
So what I did was I just set, I basically just picked the X direction and said F equals K Q1 Q2 over R squared plus K Q1 Q4 in the X direction.
Okay.
So I just picked the X. But I was kind of confused on where you go from there. Did that make sense?
Yes. All right, so do we have symmetry in this problem?
Yeah, it's a square, right? So it would be all 90-degree angles onto the corner.
Yeah, we have some symmetry since these two charges are the same. So we kind of have a line of symmetry like that. Okay. So then you're right. Let's write down our X forces for this one. What is my for the force on particle 1? What is it asking again? Okay, it's saying Oh, what is the ratio of Q over Q? Okay, so if we write down F1 of f of x, what is my total F force on this particle going to be?
Well, wouldn't it be 0? Because the F1 is 0.
Yes. So we know that the total F x force on this particle is going to be 0. So we can put that there. But now let's write out the whole expression. And I think you said it. Okay, so if I wanted to write out the whole component of the x force, what should I put here?
So it's K, Q1, Q2,
Q1, Q2
and then over R squared.
over R squared, right?
And that would be plus, and you took out K, so that would be Q1 and Q4 in the X direction
Yes.
over R squared.
And now the R's are going to be different here, right? Because, well,
Right.
so we'll say this is R1, 2, and we'll call this one R squared R1, 4.
Okay.
Because those are different distances. And then do we need anything else here with this one? Because we want the X component of the force, right?
Oh yeah, so we need like a sign or something? I mean cosine?
Yes, we need a cosine. So cosine of what angle?
45? Hold on. Let me see.
Yeah, 45.
Yes,
Yeah,
cosine of,
45?
Yeah,
Okay.
you're right.
yeah. So what's cosine of 45 equal to?
Negative 45.
Isn't it like a half?
Yes.
Yes.
I think it's a half.
It is? Okay.
Well, let me check. Mathematica, I don't remember. I think, is it 1/2?
Cosine 45. It's like 0.7071.
Let
Because it's
me,
in the middle.
I'm going to do cosine of,
Square root of 2 over 2.
what'd you say?
Square root of 2 over 2.
So it is, yes, you're right. It is cosine of 2, 2 over the square root of 2, or 1 over the square root of 2. So I'll rewrite this here. I'll have K times K1 or Q1, Q2 times, what's R1, R2? What distance is that? Oh, we'll just call it A. So it's A squared, right?
Yeah.
And then we have,
Yeah, I don't think we were given a distance.
okay, so it's just A. Then we have Q1 times Q4 over R14. And so what can we put here for R14 for our cube?
Would it be like you did in class? So it'd be like 2A squared?
Yes. So it is the square, it's this, yeah, 2A squared. That's right. And then cosine of 45 is, we said, it's pi over the square root of 2, right?
Yep.
Okay. So, and this is this plus or minus?
Should be plus.
Would it be minus? I don't know.
Well, let's look at our diagram here. So from Q1 to Q4,
Oh, okay. So it's 4 acting on 1?
so it's going to be, our X component's going to be pointing that way. So should it be minus or plus?
Minus?
Yeah, it's going to be minus. That one will be minus. And this one should be plus because it is this one I think is attractive. Maybe. Okay. All right. So we've got this, and this is all equal to 0 now. So we can we can subtract, we can get rid of our k here, and we've got a squared in both of these, so our a squares are going to go away. They just cancel. And now we've got q1 and q2. What's q1? Was that big Q or little q?
It should be a big Q.
Well, I guess we've got a big Q and a little q here. And
So then do you just solve them?
yes,
And so and you divide?
so we have big Q times and big Q and a little q over here times 2 divided by the square root of 2 equals 0. Okay, so now we can solve for them, right? Oh no, wait.
Mhm.
I think I messed this up.
Somewhere.
Oh, it's because Q4 is also a big Q. Ah, there we go. Right, because I
Right.
said Q4 was a little Q, but
Oh
Q4
yeah, right.
is actually a big Q right here.
Right.
Could you explain why you subtracted again?
Yes, because so I know that the force from this charge over here, it has to be going this way because they're the same charge, so whatever they are is going it this way. And if the net force is 0, then my other component of force has to be going this way. So one is positive and one is negative because that's the only way that the net force can equal 0.
Okay,
That's
that makes sense.
yeah. So that's why we have the difference in sign there, because they have to be equal and opposite. And so
That makes
yes.
sense. And then you can just solve from there because then there's a Q in each, so then those would cancel.
Yes.
I think, yeah.
Does it matter which, like, so they have to be opposite, but how do you know which force, either the X force going in, like to the right versus to the left on that first particle? How do you know which one is negative or positive?
Or does it matter?
So you don't know which one is negative, but one of them has to be negative.
So it shouldn't matter which one is negative. Like if we did this reverse and did like the Q1, Q4 first, and wrote that one first, would it be okay if like that one was positive and the other one was negative?
you don't know which one is which, and it doesn't really tell you in the problem.
Okay.
And in the final solution, the final answer, either big Q or little q has to be, one of them has to be negative. So then as your ratio, if you calculate then Q over big Q over little q, is this going to be positive or negative?
I think it should be negative.
Yes, it's going to be negative, because when we were doing this, we're up here, these we're just treating them as positive. We're not worrying about the sign. So this part up here is correct, but when you do this part, you need to make sure that your sign is negative because they have to be opposite charges. Otherwise, there's no way the force could be 0.
Right. Thank you.
Does that help?
Yeah.
Okay. What other questions do you guys have? Is there another problem anybody wants to look at?
I was just wondering, okay, I think I did 7A right, but I got a number and I like solved so I think I got 7A, but I haven't checked it yet. But for 7C, how do you know what like Q3 that charge is?
Ooh, let's take a look at the problem. All right, let me share my screen real quick. Okay, so it says in the figure, particle 1 of charge plus Q and particle 2 is charge plus 4Q are held at a separation of L equals 9.5 centimeters. If particle 3 of charge Q3 is to be located such that 3 particles remain in balance when released, what must AX and BY coordinates of particle 3 be, and C, what is the ratio of Q3 to Q? Okay, so did you get the first parts correct?
I don't know. Can I just like tell you what I did and then
Yes.
maybe you can, okay, so I set, you know, like I mean, I drew like the free body diagram and you know, that force one, so like, I think you'd have to stick the third particle in the middle because it has just to hold the whole system together because it has like opposite sign of the 1 and 2. Anyway, so you have the F1 on the left and F2 acting towards the right. So I just set those two forces together and I canceled out the Ks and the Q3s.
Thank you, like and subscribe down below.